now we are into the ending stretches of this learning R for your data analysis. And in this module, we're going to learn about longitudinal studies. As I indicated in my previous module, a core assumption of linear regressions is this, that when you work with your y variables, that is outcome variables, the outcome variable should be independently distributed. In other words, every value of your outcome variable should be considered to be independent of another. But sometimes this assumption does not hold. Consider, for example, let's say you want to find out what are some of the variability of temperature across, say, a fortnight. So you got temperature recorded for 15 days at a stretch. It is inconceivable that the temperature of day 1 is going to be completely independent of the temperature of the day 2, because sometimes these things, they correlate with each other. So these are not uncorrelated values that you're working with. Therefore, there should be a way in which you can do certain things. This is where longitudinal studies become very, very important, because they take into account that you can measure some things repeatedly over time, and that these values will be correlated one with the other. In other words, you can take one person and make a measurement over time. Say, for example, you take studies of student data. You measure it before you give a course, and then after you give a course of study, and then you make a measurement in terms of how much they've improved in this course. Now, these two scores are going to be correlated with each other. How do we do that? And this is where longitudinal studies and repeated measures become very, very powerful tools for you. Okay? So we'll still keep it at the form of continuously distributed data, and we'll learn how to do this. All right? Thank you.
Hello and welcome to this edition of Using R for Statistical Data Analysis. Today we're going to learn about longitudinal data analysis using R. In our previous sessions, you've read that we can use R for data analysis in in different ways. So we talked about using R for doing univariate data analysis. We talked about using bivariate data analysis where you can plot various variables together. Then we learned that you can use R for running linear regressions or linear models. And in these linear models, we had learned that you could actually have a continuous variable as a y variable or outcome variable, and a continuous variable as an explanatory variable, and you can set up both scatter plots as well as linear models. Now, one of the assumptions in linear regression models anywhere, is this, that the y variables should be independently distributed. So it's called IID, right? So they are identical and independently distributed. Now, there are situations when this is not possible. To give you an example, let us say you are trying to model over an extended period, like for 15 days, temperature of a city or rainfall in a particular over a period of time. So, and then you use some other variables to explain this, or maybe air pollution or air quality in a city over an extended period of time. Let's say you want to model air quality of a city for a year, and so therefore you got like 365 data points where you take the aggregated air quality data for a particular city on a particular day from the various measurement meters that are located in various parts of the city. And then what you want to do is this, that you would like to see whether it is the vehicle concentrations or whether it's the industrial activities or your population or some other factors that might be contributing a lot to the air quality variation. There is a day-to-day variation. But we also know that the air quality measurement for one particular day is correlated with the air quality on a subsequent day or the previous day. In other words, air quality on one particular day is not an independent entity which is separated from the air quality of the previous day or the following day. When situations such as this arise, these are the defining criterion is this, that this is one in which there are correlated observations. Another correlated observation or situation in correlated observation rise when we conduct what is known as longitudinal studies. For example, let's say you want to find out over a period of time, over a length of time, what are some issues. For example, let's say you want to study the performance of 20 students in a class who were given an instruction, and you would like to see how much they have learned by way of their scores before the instructions were given and after the instructions were given. So these are known as pre-post studies. You could argue, because same students were used for, the same students took the test both before the instructions were given and after the instructions were given. Therefore, if you would like to conduct an analysis on the basis of their instructions, it is quite possible that this time data is going to be not going to be very valid. So these are the situations where we would like to invoke a condition where we should be able to account for the play of time. So how do we do that? And that is the nature of what is known as longitudinal study. And this is something that we are going to analyze. Can R analyze that? Can you use R to analyze it? Yes, you can. Although you may not be using just the R stats, but some other packages, and we shall teach you how to use these other package in R. But the answer is that you can do that. And this is what this particular module is about. This is based on the ePathshala series. My name is Arindam Basu. I am at the University of Canterbury at Christchurch in New Zealand. And today we are going to learn about how we can use longitudinal data, or how we can study longitudinal studies or analyze longitudinal study data using R. Just a few caveats and introductory remarks in this beginning. We would like to, this is going to be basically an introduction to the topic. So we are not going to put a lot of emphasis on the statistical details and nitty-gritty of it. For that, you will need to resort to textbooks and other resources. I have included a few resources and quizzes and some other stuff along with this series of lectures, which I encourage you to use and read more. We'll talk in general about some of the core principles, but may not be much in details. We'll show you some R codes by way of a demonstration, which means that you're more than welcome to use your own data sets to do and learn from our experiences. And then we'll finally summarize the points that we have learned here. So basically our objectives here is this, that we would like to introduce some of the concepts of longitudinal studies. But the focus is on using R, because R is very powerful software, and you can use R for analysis of longitudinal studies as well. One of the requirements is that quite frequently you can actually scrape data from the web, which means that you can get data off the web and then you can use that data. And you can get data for longitudinal studies, as we shall see in a second, that these data will be in the form of multiple years or multiple time points presented as columns in data. That data is known as wide formatted data. So data in a wide format are ones in which you can get columns of data stacked one after the other, and they represent the time variable. In order to analyze data in R, well, in some software, for example SPSS, it does not matter. You can actually take a longitudinal data in the form of a wide data format, which means that if you've got multiple data points of time presented in a compressed manner, like time factor 1, 2, 3, 4, etc., that particular software will transform that data into a wide format, which means that the time variables are presented in columns and can analyze that. That's known as wide formatted data. That is usually the case with a software such as SPSS. Whereas with R, you will have to convert the wide formatted data into what is known as long formatted data. And the function with which you can do that is known as a reshape function. In reshape function, you can transform a longitudinally formatted data for longitudinal data sets from a long formatted data, which means that there are multiple observations, as much time points as are present, into a widely formatted data in which the time variables are in the form of columns. So this reshape is a very, very important concept, and we'll cover this. And then the other thing which is very important and something that you've learned, particularly with the analysis of variance, particularly with with two-way analysis of variance, the two-way ANOVA, we used interaction plots. So interaction plots are also very important when it comes to doing time-bound analysis here in this. Remember that with longitudinal data analysis here, we are not talking in terms of something like survival analysis or life table construction, because the longitudinality doesn't really work there because the outcomes are not measured repeatedly over time. So this is something that you need to keep in mind. And this is where we are once more emphasizing that when we talk in terms of analysis of longitudinal data, in this particular case, in R, we're only going to look at repeated measures analysis or repeated measures analysis of variance. So to continue with the preliminaries, what are longitudinal studies? These are essentially characterized by repeated measurements of the same individuals over time. There is also the principle of longitudinal studies. So for example, if you've got 9 pupils or 10 pupils whose performances are repeatedly measured over, say, 6 years with one measurement in every year, then you got 6 data points there, 6 time points over which they did ever measure. In this case, their gender do not change. Their ages, of course, change to some extent. But what is the area of our real point of our interest is whether there is some change with respect to their scores, whether the knowledge content changes. And maybe over these 6 years, they were given, some of them were given an intervention, others were not. Something similar also happens when we conduct longitudinal study for patients who were given medications or who were not given any interventions. How do their health-related quality of life or some outcome variables change over time? This is very, very important. So the main goal of any longitudinal study is characterization of changes in the response variable or changes in the outcome variable over time. The most important feature for repeated measurements, and particularly for longitudinal study, is this: that the measurements are correlated with each other. And the reason why the measurements are correlated, and the word correlation here means that if you take a measurement of time point 1, time point 2, time point 3, time point 4, etc., and then if you run a correlation matrix, that is, if you compare the variations or variability of these various measurements for all individuals, they're going to return high values. And the reason why this is likely to happen is because the same individual attributes are being repeatedly measured over time. Therefore, the same person is being measured. They are not independent of each other. So these measurements that we're going to use here are not independently of each other. So if we measure an individual performance in the year 1, year 2, year 3, up to year 9, or up to year n, then for each of the years, there is going to be a correlation. And this is very, very important, which means that one of the principles of a straightforward linear model, that the y variables are uncorrelated, is violated. So that assumption is not going to hold true. There are a couple of things that we would like to emphasize here. When all individuals have the same number of repeated measurements, then the study is said to be balanced. For example, if we study, say for example, cancer rates in 16 countries between the year 1996 and 2007, as we will see, and maybe one country, or for all the countries, for all the 100 countries or 60 or 70 countries or 16 countries, 20 countries, how many countries we take, for all of these countries, we have got measurements values available for every year, then that longitudinal study should be said as something that of a balanced over time. But most of the times, or sometimes, many times, we may not be as lucky. So although we have got X number of individuals for whom measurements are available, for some of them, measurements are not available for the entire period of the longitudinality of the time that we have decided to work on. So in those cases, these are known as unbalanced study designs. And essentially, when we do longitudinal studies, they proceed in two stages. So there is a feature in which there is a within individual change. So if you study individuals, you see that the same individual values are going to change over time. And then there are changes among the individuals. And both of them are important. So there is both an inter-individual change and there is an intra-individual change. And the inter-individual changes can be because of the different covariates that are taken into consideration. Say, for example, if we take 20 participants and we measure them repeatedly over 5 years, and 10 of them have been given an intervention and 10 of them have not been given any intervention, then the inter-individual change will be because of the intervention. But for all 20 individuals, it is quite possible that their scores will change over time. So individuals who are not given any interventions, they will change, and individuals who are given interventions will change as well. So in this particular case, in any longitudinal study, we'll have to account for both inter as well as intra-individual changes. Now, we describe some of the data that we're going to use in this. For this particular demonstration, we are going to use a data set which we derived from the International Agency of Research on Cancer. The International Agency for Research on Cancer keeps data for cancer rates in many different parts of the world. In this case, we're going to select 16 major countries in the world from where we get data of breast cancer in women 45 to 85 years old. And a distinguishing feature of this was that in all of these countries, women who were during the menopausal years, they had used hormonal replacement therapy. And there is some suspicion that hormonal replacement therapy is somehow associated with breast cancer. There has been a number of studies to do that. Here we are interested to find whether there were some temporal changes with the use of hormone replacement therapy and breast cancer. We also know that the incidence rates of breast cancer are related to screening age at which breast cancer screening is initiated in these countries. For some countries, breast cancer screening programs using mammography were initiated when women were 45 years or younger. In other countries, they were initiated when they were 45 years or older. 45 years age roughly is being equivalent of the age in which you set to start menopause in the women. It's also the age in which HRT concentration or HRT usage or hormone replacement therapy, abbreviated as HRT, would likely to be increased. So we would like to see whether we can use a longitudinal data analysis to study some of these patterns. In order to use this, we had to read the data first, and then we had to use a library known as LME4. It's essentially longitudinal analysis data sets. If you want to analyze longitudinally measured data or repeated measurement data, then LME4 is a very important library that you will have to use. And of course, we didn't write it here, but you need to install the LME4. So you could have to use like install.packages LME4. And then once you have installed that package, you use that package. And it's a library LME4. You could also use require LME4. The first thing that we do is we have to read the data. The data set is called brca final.2.csv, and brca final2.csv is loaded in the folder in which this tutorial occurs. So you should be able to find out in the folder where it occurs. And we have decided to remove the 8th column from the data set. So we found that for the year 1999, there was not much data that were available, so we decided to remove it from there. Okay. And you see that the data set has a number of things. This is the original data set that you're looking at when we did not remove the 1999 set of data. This came from the original spreadsheet, the CSV file. And this CSV file is in the form of, during the comma separated value file, you can see that that the years, the first column is a country. So the country here is a unit of analysis. In a second, we see the year in which, in these countries, hormonal replacement therapy reached their peak. So it's called peak HRT year, and that is a year variable. It's represented here in the form of number, and so it will be read like that, but that is when it reached a peak. And then you see what were the percentages in which the year reached their peak. And then you see the age ranges of those countries in which mammography-based breast screening programs are started. In the next few columns, you see that the incidence rates of breast cancer in these countries were given for starting with the year 1996 and ending in 2007. We see that for the year 1999, there was not much data that were available. So we had to remove the column of 1999 incidence rates, and this is what we had done when we had read the data by removing the column number 8. And as you know, this is very simple, that we specify the data frame and then we put a comma, put everything in square bracket to abstract the particular data that is important, and we put a minus sign, and then we put remove, and then we use the particular column number, and it is going to remove that particular data set. The data that you get in this format is what is known as a wide formatted data. In the next, we're going to go and remove, and we're going to convert that into a long formatted data so that it's going to work. So let's take a look at that. That is a very, very important bit when you start analyzing data, particularly longitudinal data in R. So the first thing that we do is we convert that into a long format. I'm going to read you the code and explain this. We have decided to store the initial data from a wide format into a long format by first reading the data from a CSV file and storing it into my data, and then reshaping it. So we say reshape my data. Then we add an option called varying. In the varying, what we do is this, that we, in this case, we indicate what are the time varying units, or what units are repeatedly measured. So here it is the incidence rate from 1996 to 2007 for breast cancer. And the varying variables are INC 96, INC 97, so on till INC 07, which means that incidence rates in these years. So those are the varying units. We indicate them, that these are the varying units. These varying units will be coerced into what is known as into a long format. So which means that these will be repeated in longer formats. And therefore what we call is this, that the variable which will keep these repeated units we name that variable as incidence. So v.names is a variable which will store the repetitive counts of these years that are present in the varying option. And we have decided to convert from a wide data into a long format. So we said the direction is going to be long. Similarly, if you had to convert a long data into a wide format, you'd reverse these instructions. So in this case, the vnames would change and the varying would be the incidence. Now, afterwards, we know that the first thing that we should do when we are faced with something like this is we should start with an interaction plot to see what was the variability of the breast cancer from 1996 onwards to 2007. This is done by using a plot which is known as interaction plot. So let's take a look at the interaction plot. This is the interaction plot. On the right hand side, you can see the interaction plot of the incidence of breast cancer between 1996 and 2007. The function to use is interaction.plot. And the first argument that we should pass into that function is the time. Because it's a plot and because we are not using the Wilkinson formula or Wilkinson-Rogers formula, what we are doing here is this, that we have to indicate what is going to go into our x-axis. As it stands, in our x-axis, we are going to put time. So we say my data time, my data 1 time as the as something that will go into the x-axis. And note that because time is automatically pointed in the when we converted the data from a wide to long format, it had calculated 11 time points. So 11 time points will be plotted on the x-axis. Therefore, it is our responsibility to indicate what those 11 points are going to be, and this is now indicated using the x-lab, which is the labeling of the x-axis, where I have said that 1 is equal to 1996 and 11 is equal to 2007. Then the next thing which is important is this, that country is going to be my y-axis, because what we would need to do here is this, that there are 16 units here. What we want to say is this: what is the change in the incidence rates for each country? So that's why country becomes the next unit which we have to put. So that's how many lines are going to be drawn here. And then what we do is this, that what it is that we're going to plot. We're going to plot incidence rates, which is going to be the y-axis or outcome variable. So we say my data 1, and then we start our dollar sign and incidence rate. And so when we do this, we get a series of lines that gives us the values between 1996 and 2007. Likewise, we can plot interaction plots for the years 2002 to 2007, because that is the year range in which we are interested to go and find out. Because following the decline of usage of hormone replacement therapy in 2001, there was we would like to see to what extent there have been a corresponding decline or change in the pattern of the incidence rates of breast cancer as well. So when we do something like this, one of the things that we would like to do is conduct what is known as a repeated measures ANOVA. Note here that in this particular case, we could use both a linear model, as we have been doing, or we can use what is known as an analysis of variance, or AOV. And I would like to introduce you now, this time, using the same Wilkinson-Rogers formula, but this time instead of LM or linear model, we're going to introduce you to the concepts of an AOV, or analysis of variance. Okay, so let me show you this. What the analysis of variance does then is it gives you a sense of what is the whether time is significant, whether time is a significant predictor for this. Or we could also use a linear model to see the apparent slope of the time. We can also do that, but in this particular case, we have only used the analysis of variance. So what we have done here is this, that analysis of variance, and pay close attention to this. What we try to do here is we would like to see by how much has the incidence come down over time, or whether time has been a significant predictor of the incidence, just to keep things simple. So incidence is the outcome variable, time is a dependent variable, but it is important to note that that time is nested within each country. That is, there have been like 16 countries here that we decided to study. In each of these 16 countries, there has been flow of time that has come down. So, to what extent can we account for the fact that there have been some sort of a change for these countries over this time? So that's why we have used, look at it, country/time. It does not mean that the country variable is going to be divided by time. It does not mean that. What it means is this, that time is now nested within the countries. Time is now as if contained within the countries. The countries get an importance here. And then we have indicated the data. What we had done previously is this, that from the 1996 to 2007 data, we extracted a subset of data of the long format between 2002 to 2007. We could have also done that for the wide format and changed accordingly. But be that as the case may be, we have decided to make it like a long format data, and we have plotted the summary here. So what do we see? In terms of summary, we get to see that that time variable is very, very important. Time variable has contributed to it. And I have not shown you much more details other than this, because this is just an introduction to the longitudinal model that you can do using R. And so you get a sense that by using simple strategies such as this, you can get a sense of how you can visually plot longitudinal data into R and can practice them. So to sum up, we learned some principles of longitudinal data analysis, and we learned how we can do longitudinal data analysis using R, and use an interaction summary plot in R, which will give you a sense of a graphical summary of how incidence rates or how certain things that are time variant issues can come down. Always remember to convert a wide formatted data into a long formatted data when you work with R. So this was a very simple and easy introduction to conducting longitudinal data analysis in R, and I'm sure you will learn more on this. We have included some instructions in the accompanying sheets and the data sets. So thank you, and keep exploring. Thank you very much for paying attention to this, and I hope through this series you have learned something about using R for a number of different applications that you can use. Thank you for your attention.
So this was a tour of all the things that we could do with a continuous variable and a predictor variable, which is either continuous or categorical. And we learned several different tools and tricks and things that you can do with R software. We did not cover the statistical details of it, which I trust you will learn from other things. I hope you learn how to use R for your data analytical tasks in this series. And goodbye, and keep learning till we meet again.